So our lesson on ellipses, we're going to kind of cover ellipses and then come back to circles as well, because an ellipse and a circle have a lot of commonalities and one major difference. And when we have enough knowledge of our different conics, including hyperbolas, we're going to be able to look at a general conic form and then do a little algebraic manipulation and then determine whether we're looking at a parabola, ellipse, hyperbola, or a circle. So that's the grand finale of this unit, right? So an ellipse is oval in shape, but basically it's a circle that got stretched out, if you want to think of it that way. And we have some common vocabulary terms that are going to pop up here in the next couple sections. Foci, two focus points. They are two fixed points, and the distance between them is constant. We're going to talk about a concept called eccentricity coming up, and that's going to tell us how circular our ellipse is in comparison to a true circle. I don't think that comes up until the second half of this section, so that's the next video in line here. This is a visual for how an ellipse is developed. Remember, we had something kind of similar for a parabola. A circle is a really basic, pencil with a string, a radius, a fixed distance between around the center. If we kind of read through this concept here, consider the length of the string tracked at foci. Okay, so if you attach the ends of a string to the two focal points, and then you could take your pencil and literally drag it around. So it's kind of like the circle creation that you did when you were a small child, except because the distance of D1 and D2 are going to be different depending on where you are on the ellipse perimeter. That's why we get this elongated, irregular shape. It's not quite a circle. So it's kind of a neat diagram, a neat activity, which I know you guys are going to ask me, can we do that activity? Until I answer that, yes, go ahead at home on your own time. All right, so here's some more vocabulary here. We have the center of an ellipse, just like with a circle, but then we're going to have major and minor axes. The major axis is referring to the longest part of the ellipse, and then the minor axis would be the other one. So, because remember it's not a circle, you do have a different size for the major and the minor axes. And we're going to have vertices and co-vertices. So, the major axis, the longer one, we call his endpoints the two vertices. And then co-vertices would be the smaller axes endpoints. Alright, so this is on your notes. This is exactly what you see on your notes page. And we have the same formulas that appear on your green formula sheet for an ellipse, and I believe there's two different forms on your formula sheet. And I don't know if it's more confusing or less confusing that they have the two forms, because they're really the same thing, right? The only difference is in which direction is your major axis running. So this version of the formula, where they have the x minus h squared term first with the a squared below it, that would be if you have a horizontal ellipse. So the longer axis is going in the x direction. Good morning.
How's everybody? Good, will somebody said?
So if we have the y minus k squared term first, and they're going to say the a value goes with the major axis, that means you have a vertical ellipse. Hello. So the vertical axis is the major axis. Now, in either case, they're going to determine that the a squared term always comes with the first fraction, the major axis. But because it's an addition sign in between the two terms, I mean, we have a commutative property that's kind of taken effect here. So you're not wrong if you reverse the order of these two fractions. You just have to be careful that the a in this next formula is from the major axis, because if you don't have the larger term first in a subtraction problem, you're going to get a negative value. It's not going to make any sense. So in my brain, because things get backwards all the time, I just remember that in order to find the distance of C, we're going to have to take the major axis squared minus the minor axis squared. So the A and the B don't really mean anything to me, because I'm probably going to get it backwards. Anyways, this is on your notes. This is also the information that you'll see on your green sheet, and has a nice visual. Just like with our parabolas, the formulas for how to find things changes based on whether it's in a parabola it was horizontal and vertical parabola, but now we have a horizontal and vertical major axis ellipse. So when we see a visual of this, it's going to make a lot of sense, I think. And this is one of those examples that's already done in your notes. So follow through with me anyways. We have y minus 1 squared over 25. So this is our major axis. So we have a vertical parabola, a vertical ellipse. This is a squared. This term right here is b squared. And then the center, like everything else in our conic section, can be found by finding h and k. Now whether the order is reversed, it doesn't matter because h is always with the x value, and then k is always with the y value. So our center is still going to be at negative 2, 1. And of course that would be plotted. And oh, why do they do this to me? They're counting by 2's again. Negative 2, 1 would be right here is the center of your ellipse. And then what I usually do next is I plot the vertices and co-vertices. And I don't really use a formula to do that. But if you want to use a formula, you can. So the 25 is a squared, meaning that if I square rooted that, the distance of a is 5. So in our major axis direction, which I know is vertical, I'm going to travel up and down 5 units. So they plotted their vertices at, and again, they're counting by 2, so remember this, but it's at negative 2, 6, which they could have found using the formula, of course. We all love formulas. And then negative 2, negative 4, going down 5 units. So for the co-vertices, I notice that the b squared value is 9, which means my b value, or my minor axis direction, is 3 in each direction. So moving right and left 3 units. They plotted this co-vertex at 1, comma 1, and then this co-vertex at, where are we at? I already forgot. Oh, negative 5, 1. Again, we could have used our formulas, which are these guys here. But, you know, I really hate when these count by 2s. It just really bothers me. Alright, the thing they haven't found for us yet, at least not on this screen, are the location of the foci, which are those fixed points that are inside of our ellipses. It's going to be a distance of c units on the major axis from the center. So if we could figure out who c is, we're going to be in business. So remember the formula was c squared equals a squared minus b squared. So if we square root that equation to find c, we're going to find out that c is, what is that, 25 minus 9? So square root is 16, which is 4. So on the major axis, if we go up and down 4 units, where are we at again? 1. Alright, so going up 4 units would be up here at 5. Down here, 4 units. Hello. Now for the foci, if you use the formula, which I think, you know, might be in our best interest at this point, the foci's formula is at h, comma, k plus n minus c. So this is for a vertical ellipse. So h was negative 2, and then we're going to take 1, we're going to add and subtract a distance of 4 units. So what I do now is then I actually separate them and write their 2 ordered pairs here. Negative 2, comma 5, and negative 2, comma negative 3. Alright, so we have all the pertinent information. We could have drawn our ellipse, and it was already done for us. Oh, that's okay. Thank you. So that was the same question, which is already done for us. So let's move on to number 1. Alright, so here, the first thing I find is the center. Which I shouldn't call C, because there's another C coming up in the problem, So the center is at HK, so this one's really boring. It's at 0, 0. And then what I usually do next is I determine the orientation of the ellipse. Hello. And it's vertical, because the larger axis here is with the Y. So I just kind of draw myself a little note that it's going to be vertical in orientation. The A value is a 4. The B value is a 3. And then I think we can at least plot those pieces of information. Again, they're counting by 2's. Why do they hate me so? Alright, so we have a center at 0, 0, and then a major axis of 4 units, and that would be vertical, right? So 4, down 4, and then a minor axis of 3 units, so in the middle here. And then we are supposed to draw an ellipse by connecting here. Maybe what I need is that pencil and string trick, right? Now, it's pretty good for me, but for a normal person, it's a very poor job. So we can find the location through the formulas, but we already plotted them, so if you want to label them, you sure can. Our major vertices are at 0, 4, and 0, -4. And then our minor vertices, or co-vertices I believe we call them, are at -3, 0, and 3, 0. Again, formulas work great, I just don't really need them for this problem because we're graphing it. The next thing we have to find is the value for C, which is the distance from the center to each of the foci. So C is the square root of a squared minus b squared. So a squared 16 minus b squared would be square root of 7. So for the foci, for a vertical ellipse, is at h comma k plus n minus c. So for us, that means we have 0 comma 0 plus square root of 7 and 0 minus square root of 7, so 0 square root of 7. Yeah, gross. Alright, so square root of 7 is between 2 and 3 somewhere, which makes sense for where I'm looking. So they're somewhere roughly there. If you wanted a more accurate description, you probably want to type that in your calculator and get a decimal, but let's be honest, my graph is really ugly, so it doesn't matter. And they did want me to state the vertices and the foci, and we graphed it, so looks like we're good. Okay, this next one. The larger value for the major axis is under the x term, so that means we have a horizontal ellipse. The a value is going to be an 8, the b value is a 5, and the center is at hk, so -5, -2. So my major length vertices, I'll use a formula on this one if you want. It would be, geez, I was weird at the formula. H plus and minus a, there we go. H plus and minus a comma k, which makes sense for the horizontal one. So using that formula, -5 plus and minus 8 comma -2, gross. So the location of them are -5 plus 8 would be 3, -2, and -5 minus 8 is -13, -2. So I don't really love using the formula to find vertices or co-vertices for that matter. Let's go ahead and find the co-vertices while we're at it. Co-vertices formula is h comma k plus and minus the b value. So using our information, it would be -5 comma -2 plus and minus b, which is 5. So the two locations for our co-vertices are, let's see, -5, 3, and -5, -7. Alright, let's get this stuff plotted. So our center, I keep calling it C and I really shouldn't. Our center is at -2 skip. -5, -2. And then for our major axis vertices, we're going to be plotting 3, -2, and -13, -2. Lovely. Alright, so 3, -2 would be right here. Oh man, there is no way I'm going to get. Alright, that's not right. I screwed something up. Alright, back up. This is at -5, 13. Okay, so 10, 12, so it's right here. There we go. There's no way I'm going to be able to graph this and make it look like an ellipse. So, anywho, alright, -5, 3 is our co-vertex, and -5, -7 is our other co-vertex. Now, I'm going to attempt. Oh, it's going to be so bad. Alright. So my ellipses look like footballs. They're not supposed to. Let's find the value for the distance between the center and the foci. So c squared equals a squared minus b squared. So c is square root of 64 minus 25, which is square root of 30. No, 39. I always get that one wrong. 39, yeah. Alright, gross. So again, that's some decimal. 6 point something. I think I wrote it down here. No, I didn't. 6 point something. That's all I know. 6 point. I can make it up, but it's 6 point something. Alright, so measuring 6 units forwards and backwards is great, but they do want me to state the location of the foci. So with that being said, we do need to use the calculation. For a horizontal ellipse, the foci are located at H, and then we're going to add and subtract the C value, and then stay at the same K value. So for us, that would be H is -5 plus and minus gross the square root of 39, comma, -2. Okay, I'm not even going to bother breaking that apart. If I truly wanted to plot accurately, I'd be converting the square root of 39 to a decimal and getting like a decimal location. I'm just going to kind of fudge this and count backwards and forwards 6 units. But remember, they're counting by 2s. So 2, 4, 6, so like right here somewhere. 2, 4, 6, right here somewhere. Alright, there we go. So they are a distance of C unit from here to here. They're also equidistant from the major vertices. Actually, they're equidistant from a whole bunch of stuff, but we're going to do some applications in a second where it would make more sense to say the distance from the edge of the ellipse rather than the center. Okay, number 3. Same song, different dance here. So I'm going to, we'll do 3, and then I think I'm going to skip 4 because they're all kind of the same. So the center, which I'm going to get smart finally and label it as center, is located at -2, -1. And then our A value, our major axis distance from the center, is 5. Our minor, or B value, is 3. So when I go to find the vertices along the major axis, major vertices. Okay, got a delay. If I use my formula for major vertices for a, let's say this is a horizontal parabola, that would be H plus and minus the A value, comma, comma K. So for us, that would be -2 plus and minus 5 units, comma, -1. So actually coming up with 2 separate ordered pairs, -2 plus 5. Let's see, it would be 3, -1, and -7, -1. Alright, and then for our minor vertices, co-vertices, that formula for a horizontal parabola would be H, comma, K plus and minus the B value. So, -2, comma, -1, but we're going to add and subtract 3 units. Again, I think they're just easier to plot, but either way you have to give me the ordered pairs, so it's up to you. Alright, -2, comma, 2, and -2, comma, -4. So 2. Alright, let's plot this stuff. Counting by 2s again. -2, -1, there's your center. Major vertices are at 3, -1. And then -7, -1. Oh, for Pete's sake, -1. I quit. I'm gonna vote that we no longer count by 2s ever again. I hate it. So our minor, our co-vertices are at -2, 2, and -2, -4. And again, I'm supposed to somehow magically create an ellipse. But this side's looking really good, and that side looks awful. Okay, what's the location of our foci? So, for a horizontal parabola. Oh, we need to find C real quick. So, C is the square root of 25 minus 9. Square root of 16 is a 4. So, for a horizontal parabola, the foci is located at H plus and minus C, comma K. So, for our ellipse, let's H again, -2 plus and minus 4 units. And then we're going to stay at -1. So, the 2 ordered pairs for the foci are 2, -1, and -6, -1. 2, alright, 2, -1, there we go. I forgot we're counting. Alright, -6, -1 right there. It's lovely. Alright. Yay. Skipping 4, I'm done. Alright, this one is already done for you on your notes, but we should kind of watch and see the magic happen here. they are not looking at an ellipse in standard form. This is in general conic form, which we know is awful. So the first thing I want to look for is make sure that there's not a common factor between every single term. And for a minute I got excited because I thought they could all be divided by something, but then this 9 kind of screwed everything up. So we have to complete the square by collecting the x's and y's together, just like we do with a circle. But at the very end, we're going to have to divide by a number, because have you noticed at the end of the equation for standard form, if it's not a circle, this number is going to be a 1. So we'll talk about that in a second. Alright, the x's. 4x squared plus 24x. We're going to have to complete a square in a second. We'll talk about the 4 in a minute. And then same thing with the y's. So we have plus 9y squared minus 36y. We're going to have to complete his square. We'll talk about the 9 in a minute. And then this 36 basically needs to move out of the way. So I'll subtract 36. Well, we have to balance out all this completion of squares that we're doing. And we've got the added bonus fun of having things that are not 1 in the first term. So first thing we need to do is notice that there is a common factor of 4 in this blue group. So if I factor the 4 out, now we have x squared plus 6x, which we will complete. And similarly for the red group, we have to factor out a 9. So we have y squared minus 4y plus equals, I already have this negative 36 over here, and then we will complete the square again and again. Balance it out. Alright, let's talk about the blue blink. Half of 6 is 3, 3 squared is 9. But this is not really a 9. This is really a 4 times 9, so it's really a 36 that we're balancing. And then half of this negative 2 squared is 4. It's not really a 4, though. It's really a 36. Apparently it's the number of the day here. Alright, so this blue group, when I write it in vectored form, this is 4 times x plus 3 squared. And then plus 9, this is really y minus 2 squared. Negative 36 plus 36 plus 36 is 36. It's fun. I guess we could have just left that 36 alone. Oh well. And then this is what I'm talking about. So this is not a circle because there's numbers in front of these factors. They can't be there, which means it's one of our other conic section things. So what we're going to do is whatever this number is, you're going to divide by it on every term. And that creates the formula that we have been using today, which is going to be the ellipse formula. So this becomes x plus 3 squared over 9 plus y minus 2 squared over 4 equals a 1. We definitely have an ellipse. It's even in the right form. That was wonderful. We should be able to identify all the pertinent pieces, right? So, oh, they don't even want that. They just wanted me to write it standard form. Done and done. Okay, so more fun with completing the square. Let's talk about doing that again. And this is fun because it doesn't tell me that we have an ellipse. We might not have an ellipse, so they want me to identify what conic we're looking at. So right now your only choices are circle, parabola, and ellipse. We'll learn about hyperbolas next. So it won't be that. Alright, let's talk about the fact that they're not completed, they're not grouped. I'm going to group all my x's together. Oh, they're kind of already grouped. And then same thing with the y's. And then, oh, someone kind of already set us up real nice here. Let's keep going. Alright, so we have y squared plus 2y. There's no coefficient there, so leave a blank. I'm going to save myself a little time here. I am going to group this, the blue parts here, but there's a common factor of 6 that we're going to need to take out to complete that square. So x squared minus that's going to become not 6, it's 4. Hello. I need a nap already. Complete his square. Some kind person already moved the 5 over. That was nice. And then we're going to have to balance out our completing the square problems. Alright. I don't know why I did that in blank. Alright, back here. This first blank, half of this 1 squared is 1. And it really is a 1 because there's no common factor taken out. And then here, half of 4, 2 squared is 4. But this 4 is really a 24. So what we have right now is this red group is y minus 1 squared. No, it's not. It's y plus 1 squared. This blue group is 6 times x minus 2 squared. And then 5 plus 1 plus 24 is 30. So we can't have a circle because of this factored out term here of 6, so that means I must have an ellipse. but we're not quite in the right form because remember for ellipses this number has to be a 1. So we're going to divide everything here by a 30. And thank goodness they don't want me to find anything because that would require me to use really funky fraction and radical thing, not fractions, radicals. Just making sure. Yeah, they just want, okay, we're good. Y plus 1 squared over 30. 6 over 30 reduces to a 5, so x minus, oh jeez, plus x minus 2 squared over 5, and then 30 over 30 is a 1. So for sure we have an ellipse. This happens to be a vertical ellipse. I don't care though, because they don't say to find anything, so we're going to move along. Same thing. Don't just assume everything's going to be ellipse today, though. They might not. We will see. Alright, let's check out this one. Grouping my x's and y's. Someone kind of already did that for me. So I just need to complete the square. Oh man, it's like your birthday. There's nothing to factor out. Same thing here. There's nothing to factor out here either. The 14's already moved over. That's nice. So now we just have to balance out the completing square questions. So with your limited knowledge of the conic sections, maybe you kind of already know what this is going to be. If this was like an SAT question where it said identify the conic and give you choices of hyperbola, ellipse, circle, whatever, you'd be done if you already knew what this was. But these are our notes. There's no sense in skipping. Alright, completing the square here will give us a 1. Completing the square in the blue term, let's see, 12 squares, 144.
Caden Springer, please come to the main office.
And then we end up with y plus 1 squared plus x minus 12 squared equals, what we got here, 15, yes, I should be able to add that. 9, 5, 159. Alright, so we don't have to find anything other than identify the conic. There's no values in front of these factors to divide by, so we have a good old circle. Because the distance is just going to be the length of the radius, which is square root of 159, which is gross. Good thing we don't have to graph it. Alright, this next one, same direction. So, first thing I notice is there's only one squared term in the entire problem. So I will be completing the square on this, and because of the fact that there's only one variable that has a squared component, I already know it's going to be a parabola. But again, these are our notes, so let's go through it, and maybe at least we'll discuss what kind of parabola we had, because maybe that's interesting to us. Alright, so I don't really like when they're all on the same side, because remember our parabola form, they have all the y's on one side of the equation factored. So I'm actually going to move all this over here. And this becomes y squared plus 4y, we're going to complete the square, equals, and then when I moved everything over, I have a negative 4x plus an 8, because I subtracted everything over. But remember how that 4p value is factored out of that term? So I'm going to go ahead and do that. I'm going to factor out a negative 4 right here. And that will got a little excited about that. Alright. A negative 4. There we go. That leaves me with x minus 2. Good, good, good. Alright, so, oh, you know what though? I should have, let's hold off on that. I need to back up a minute. I forgot we didn't complete the square yet. I apologize. Okay, so 4. Alright. Okay, now I'm going to worry about factoring and completing the square. So this is y plus 2 squared. This is negative 4x plus 12, but again I have that common factor of negative 4 I will be taking out of that. So this ends up being x minus 3. So this is the standard form of the parabola that we have been using, where I can clearly see that 4p value that's out in front of the factor. I'd be able to tell the vertex, and I could figure out the distance for p. I could find all sorts of stuff, but I don't have to, because all it wants is what is it. And this is a parabola, and more specifically, the type of parabola we have is a horizontal parabola because the y value being squared. Ooh, for bonus points, if you can tell me whether it opens right or left, that'd be great. So because this term is negative 4, that means it's going to open left. That wasn't asked of us, but man, it's good to put some thoughts together here at the end of our lesson. Alright. Literally the end of our lesson, I guess. There's 2 more questions. Let me look at them and see if we need to continue on. Oh, there's only one more question. I lied. Spoiler alert. It's an ellipse. It's a really good one, too. Alright, I'm going to end the lesson. The second part of our lesson is going to be more on ellipses and circles. It's going to be a little more complicated, where I give you some clues, like where the foci are located, and then you have to go back and find the equation of the ellipse. So, fun times ahead.